13 billion years ago, something happened that shouldn't have been possible. The universe was barely 500 million years old, just awakening from its cosmic night, when galaxies as massive as the Milky Way suddenly ignited into being. And now, the James Webb Space Telescope has found not one or two, but 300 of them. They burn a deep blood red in the infrared, filled with billions of stars that shouldn't exist yet. By every model of cosmic evolution, this is impossible. Dark matter hadn't yet coalesced. The hydrogen fog of the early universe should have smothered their light. But there they are, ancient beacons that break the known laws of formation. If you're drawn to mysteries that defy science and rewrite our understanding of reality, hit that like button and subscribe, because this is where the story begins. Imagine a newborn speaking in full sentences moments after birth. That's what Webb just witnessed in the early universe. Researchers from the University of Missouri, scanning 4 deep space fields, discovered 300 objects glowing far brighter than physics should allow. These aren't just distant galaxies, they're cosmic paradoxes, windows into a universe far stranger than we ever imagined. Here's the problem. When you look deep into space, you're seeing the past. Light takes time to travel. The farther away something is, the older the light reaching us. These objects sit so far away that we're viewing them as they appeared 500 to 700 million years after the Big Bang. The universe itself is only 13.8 billion years old. That means we're watching events from when everything was practically brand new. According to our current understanding of physics, galaxies need time to grow. Stars must form from collapsing clouds of hydrogen and helium. Gravity needs to pull matter together slowly over millions of years. Dark matter halos have to assemble first, creating invisible scaffolding that holds ordinary matter in place. The process follows specific rules about how fast things can happen, but these 300 objects ignored those rules completely. They shine with the brightness of mature galaxies packed with billions of stars. Some contain nearly as much stellar mass as our modern Milky Way. That's like finding a fully grown oak tree sprouting from soil that was tilled yesterday. The timeline doesn't work. Hao Jingyan, the astronomy professor leading this research, calls them candidate galaxies because scientists need more data to confirm exactly what they are. Right now, they appear as tiny red dots in Webb's infrared images, but their spectral signatures suggest they're massive stellar cities that assembled at impossible speed. The discovery challenges something called the Lambda CDM model. This is our best framework for understanding how the cosmos evolved from a smooth soup of particles into the structured universe we see today. The model predicts that small structures form first, then gradually merge into larger ones. Dwarf galaxies should come before giant. Baby stars should come before mature stellar populations. These 300 objects flip that script entirely. They suggest the early universe was far more dynamic and violent than we imagined. Matter might have clumped together through processes we haven't discovered yet. Or perhaps our fundamental assumptions about cosmic evolution need serious revision. Over 80% of these mysterious objects fall into a category astronomers call extremely red objects. Their light is strikingly brighter in certain infrared wavelength compared to others. This redness tells us something crucial about their age and distance, but it also deepens the mystery about how they got so bright, so fast. Something in the infant cosmos was accelerating galaxy formation beyond anything our physics allows. The question keeping astronomers awake at night is simple. What force could possibly work that quickly? Before these impossible galaxies could form, the universe spent hundreds of millions of years in complete darkness. This wasn't the darkness of a moonless night. This was absolute cosmic blackness. No stars existed. No galaxies glowed. The entire universe was a cold, lightless void. The Dark Ages began 380,000 years after the Big Bang. At that moment, the universe had finally cooled enough for electrons to bond with hydrogen nuclei, creating the first neutral atoms. This process, called recombination, changed everything. Before recombination, The universe was an opaque plasma, where photons constantly scattered off free electrons. Light couldn't travel more than a few feet without hitting something and bouncing away. When neutral hydrogen formed, photons suddenly had room to move. The universe became transparent for the first time. But here's the twist. There was nothing creating new light. The energy from the Big Bang was still racing outward in all directions, but it was fading fast as space expanded. Within a few million years, the cosmos went completely dark. Imagine floating in this primordial void. In every direction you look, you see nothing but blackness. No stars twinkle, no nebulas glow. The only thing filling space is a thin fog of neutral hydrogen gas, invisible in the dark. This gas absorbed ultraviolet light, making the darkness even more complete. A single photon trying to escape would get trapped, absorbed by hydrogen atoms before traveling any meaningful distance. Dark matter was there. We can't see dark matter because it doesn't interact with light at all, but its gravity was already at work, pulling the hydrogen gas into invisible filaments and clumps. These dark matter halos were slowly building the foundation for future galaxies. But without stars, without any light source, this construction happened in total silence and darkness. The Dark Ages lasted somewhere between 400 million and 600 million years. Scientists debate the exact timeline because we can't observe this period directly. Light from that era never reaches us. The hydrogen fog trapped it all. What we do know comes from computer simulations and by studying what came after. During these dark centuries, temperature in the universe dropped to nearly absolute zero. The hydrogen gas drifting through space reached temperatures around 450 barometer. Everything was cold, dark, and still. The universe was waiting. But beneath this apparent calm, gravity kept working. Dense regions of dark matter grew denser. Hydrogen gas fell into these gravitational wells, piling up, getting compressed. Pressure built in these gas clouds, and when pressure and density reach critical thresholds, something spectacular happens. The first stars ignited. These primordial suns, made entirely of hydrogen and helium, burned incredibly hot and bright. They were probably 100 times more massive than our sun. They lived fast and died violently, exploding as supernovas within just a few million years. But their light had already changed everything. Those first stars ended the cosmic dark age, and somehow, within just a few 100 million years of that first light, 300 massive galaxies were already shining. The timeline feels impossibly tight. James Webb doesn't just take pictures of distant space. It functions as a time machine, capturing light that's been traveling toward us for most of the universe's existence. Understanding how this works reveals why these 300 galaxies are so shocking. Light moves fast. In 1 second, it travels 86,000 miles. That sounds instantaneous until you consider cosmic distances. The nearest star beyond our sun sits over 4 light years away, meaning its light takes 4 years to reach us. When we see that star, we're actually seeing what it looked like 4 years ago. Now scale that up to galactic distances. The 300 mysterious objects Webb discovered sit roughly 13 billion light years away. Their light has been racing through space for 13 billion years. When we see them now, we're watching events that happened when the universe was only 500 million to 700 million years old. We're literally looking backward through time. But there's a complication that makes this even stranger. The universe isn't static. Space itself is expanding, stretching like dough in an oven. As space expands, the light traveling through it gets stretched too. This stretching shifts the light's wavelength toward the red end of the spectrum, a phenomenon called redshift. Think about an ambulance siren. When it drives toward you, the sound waves compress and the pitch rises. When it drives away, the waves stretch and the pitch drops. Light works similarly. Objects moving away from us have their light stretched to longer, redder wavelengths. The faster they recede, the more their light redshifts. For extremely distant galaxies, this redshift is dramatic. Light that left them as ultraviolet or visible blue light gets stretched so much it becomes infrared by the time it reaches Earth. This is why Hubble Space Telescope, which primarily sees visible and ultraviolet light, missed many of these early galaxies. They had redshifted beyond Hubble's range. James Webb was specifically built to see infrared light. Its 18 hexagonal mirrors collect infrared radiation, invisible to human eyes. Its instruments can detect wavelengths from 6 to 28 micrometers. That range is perfect for finding the most distant galaxies whose light has been stretched by cosmic expansion. The telescope measures how much a galaxy's light has redshifted. This measurement tells astronomers the galaxy's distance, and therefore how long ago we're seeing it. A galaxy with a redshift value of 10 existed roughly 13.2 billion years ago. Higher redshift means more distant and more ancient. Webb's near-infrared camera captured the 300 mysterious objects during deep field surveys. These surveys stare at tiny patches of apparently empty sky for hours, collecting every photon possible. What looks empty to our eyes explodes with distant galaxies in Webb's infrared view. Each of those 300 red dots represents a galaxy so far away that their light has been traveling since before Earth existed, before our sun formed, before most of the stars in our galaxy were born. We're witnessing the cosmic dawn itself. But here's what troubles scientists. These galaxies shouldn't be visible at all yet. Finding the oldest galaxies in the universe requires clever detective work. Astronomers can't just look for faint objects. They need a method that specifically identifies extremely distant, extremely old galaxies while filtering out everything else. That's where the dropout technique comes in. The method exploits a property of hydrogen gas. Hydrogen atoms absorb ultraviolet light at a very specific wavelength called the Lyman limit. This absorption happens at 91.2 nanometers. When ultraviolet light from a distant galaxy passes through clouds of neutral hydrogen in the early universe, all wavelengths shorter than the Lyman limit get absorbed. The galaxy essentially drops out of view at those wavelengths. Here's how astronomers use this effect. They photograph the same region of space using multiple filters, each capturing a different color or wavelength of light. A galaxy might appear bright in redder filters, but completely disappear in bluer ones. This vanishing act signals that we're seeing a galaxy so distant that its Lyman break has redshifted into the visible or near-infrared range. Bang Jiang Sun and Jing Yan used this technique on James Webb data. They examined over 500 square arc-minutes of sky captured by Webb's near-infrared camera. They were specifically looking for objects that appeared in longer wavelength filters, but dropped out in shorter ones. The dropout pattern acts like a cosmic fingerprint, identifying the earliest galaxies. The technique works because the farther away a galaxy sits, the more its light stretches. For a galaxy at a redshift of 7, its Lyman break has shifted into the near-infrared. For even more distant galaxies at redshifts above 10, the break shifts further into the infrared spectrum. By carefully comparing images taken through different filters, astronomers can estimate how far the Lyman break has moved, and therefore how distant the galaxy is. This method isn't foolproof, though. Other types of objects can mimic the dropout pattern. A dusty nearby galaxy might look red and fail to appear in blue filters. A quasar or active black hole could produce similar colors. That's why astronomers call these findings candidate galaxies rather than confirmed ones. Additional observations are needed to rule out imposters. The researchers found 300 candidates this way. Each one showed the telltale dropout signature. They appeared bright in some infrared wavelength, but vanished in others. The pattern suggested these objects sat at incredibly high redshifts, meaning they existed very early in cosmic history. But something was wrong. The number of dropout candidates was higher than expected. Previous surveys and theoretical models predicted fewer massive galaxies in the early universe. Finding 300 bright ones in a relatively small area of sky suggested the infant cosmos was more crowded than anyone thought possible. Even more puzzling was their brightness. These weren't faint smudges, barely visible at detection limits. Many glowed powerfully in the infrared. That luminosity implied they contained enormous numbers of stars, perhaps billions of them. How did so many stars form so quickly? The dropout technique had revealed something unexpected. The early universe was apparently filled with large galaxies, faster than physics should allow. When you look at images for the 300 mysterious objects, one feature dominates. They're red, not pink, not orange, deep dark red. This coloration isn't decorative. It's a critical clue about their age and nature. Over 80% of the dropout candidates fall into a category called extremely red objects. The technical definition is straightforward. Their brightness in one infrared filter exceeds their brightness in another infrared filter by more than 2 magnitudes. In practical terms, they're about 6 times brighter at longer infrared wavelength compared to shorter ones. That's an enormous color difference. Why does this redness matter? In astronomy, color reveals history. When stars first form, they burn hot and blue. Young, massive stars emit most of their energy as ultraviolet and blue light. As stars age, they cool and redden. Old stellar populations dominated by red giant stars produce more red and infrared light. Red galaxies typically contain older stars, but these 300 galaxies aren't red because they're old in the normal sense. They existed when the universe was incredibly young. Their redness comes from redshift combined with possible dust. As cosmic expansion stretches their light across billions of years of travel time, wavelengths that started as visible blue light get pushed into the infrared. Ultraviolet light becomes visible red. Visible red becomes near infrared. The more distant a galaxy, the more extreme this effect. For objects at redshifts around 7 to 10, light emitted in the ultraviolet ends up observed as mid-infrared. This is why Webb's mid-infrared instrument found additional detail in 13.7 of the candidate. These galaxies were so distant, their light had stretched completely into the mid-infrared range. Dust plays a role too. If these young galaxies already contain significant amounts of cosmic dust, that dust would absorb blue and ultraviolet light while allowing red light to pass through relatively unimpeded. This would make them appear even redder. But here's the problem with that explanation. Where would the dust come from? Dust grains in space are made of heavy elements like carbon, silicon, and iron. These elements don't exist naturally. They only form inside stars through nuclear fusion. When massive stars explode as supernovas, they scatter these heavy elements into space where they can condense into dust grains. But this process takes time. Multiple generations of stars need to live and die before significant dust accumulates. For these galaxies to already be dusty at such an early epoch implies incredibly rapid stellar evolution. Stars formed, lived entire lifetimes, exploded, and created dust all within the first few 100 million years of cosmic history. That's possible, but requires star formation rates far exceeding anything we observe in modern galaxies. The redness also helps astronomers estimate distances by measuring exactly which wavelengths each galaxy appears in and which it drops out from. Researchers can calculate its redshift value. This gives an approximate distance and age. For the 300 candidates, the calculations suggested 2/3 sit at redshifts between 1 and 4, meaning they're closer and younger than initially thought. But 1/3 potentially sit at much higher redshifts above 7 or even 10. Those are the truly problematic ones. If confirmed, they represent massive galaxies that formed impossibly early. The blood red glow isn't just aesthetically striking. It's evidence of cosmic processes happening faster than our models predict. Building a galaxy takes time, or at least it should. The 300 objects Webb discovered seem to have skipped several steps in the cosmic construction manual. Understanding why requires looking at how stars actually form. Star formation begins in giant molecular clouds, vast regions of gas and dust floating in space. These clouds are mostly hydrogen, with traces of helium and heavier elements. Gravity slowly pulls the gas inward, creating denser clumps. As a clump collapses, it heats up. When the core reaches about 18 million degrees Fahrenheit, nuclear fusion ignites. The star is born. This process has limits, though. You can't just cram infinite amounts of gas into stars instantly. Physics imposes speed limits on star formation. The main bottleneck is called feedback. When massive stars form, they produce intense radiation and powerful stellar winds. This energy blasts surrounding gas away, making it harder for new stars to form. When massive stars die, as supernovas, the explosions scatter even more gas. These feedback mechanisms act like pressure relief valves. They prevent gas clouds from collapsing too quickly. Without feedback, all the gas in a galaxy might turn into stars within just a few million years. With feedback, the process stretches over billions of years. Modern galaxies convert gas into stars at relatively modest rates. The Milky Way produces about 3 new solar masses of stars per year. Some active galaxies manage 10 to 20 solar masses annually. A few extreme starburst galaxies hit 100 solar masses per year, but these are rare and short-lived. Now consider what the 300 mysterious objects accomplished. If they truly contain stellar masses comparable to our Milky Way, that means billions of solar masses worth of stars. Our galaxy has roughly 100 billion stars. These early galaxies appear to have assembled similar numbers within just a few 100 million years. Do the math. To build 100 billion solar masses of stars in 500 million years requires an average star formation rate of 200 solar masses per year, every single year for 500 million years straight. That's 10 to 20 times faster than the most extreme starburst galaxies we observe today. And remember, this rate needs to be sustained. Most starburst galaxies burn out quickly. Feedback from all those massive young stars blows away the remaining gas, shutting down further star formation. These early galaxies somehow avoided that fate, or overcame it through processes we don't understand. One possibility is that star formation worked differently in the early universe. The gas was denser, it hadn't been enriched with heavy elements yet. Perhaps primordial gas collapsed more efficiently than modern enriched gas. Maybe the first stars formed in massive clusters rather than individually, allowing higher formation rates. Another theory suggests these galaxies experienced multiple intense bursts of star formation rather than steady growth. They might have gone through violent episodes where star formation rates temporarily skyrocketed to 1,000 solar masses per year or more. A few brief bursts like that could account for their large stellar population, but both explanations require special conditions or mechanisms that current models don't include. Standard galaxy formation theory assumes gradual feedback-regulated growth. These 300 objects tell a different story. They formed stars faster than the universe should have allowed, and that's making astronomers question everything. Every galaxy we observe today sits inside an enormous halo of dark matter. This invisible substance doesn't emit light. It doesn't interact with ordinary matter, except through gravity. But its gravitational pull is what holds galaxies together and shapes their formation. The problem is that 500 million years after the Big Bang, these dark matter structures shouldn't have existed yet. Dark matter makes up about 84% of all matter in the universe. It formed shortly after the Big Bang, likely consisting of exotic particles we haven't identified. Immediately after the Big Bang, dark matter was spread relatively evenly through space with only tiny density variations. Over time, gravity amplified these small differences. Think of it like cream stirred into coffee. At first, the cream is almost evenly distributed, but if you let it sit, tiny currents and differences in density cause it to clump. Dark matter clumps the same way, but much slower. The densest regions pull in more dark matter from their surroundings, growing larger and denser over millions of years. These growing clumps of dark matter create gravitational wells. Ordinary hydrogen and helium gas falls into these wells, gathering in the centers. As the gas becomes dense enough, stars can form. The dark matter halo acts like scaffolding, providing the gravitational structure that holds the galaxy together. This process follows a hierarchical timeline. Small dark matter clumps form first, creating dwarf galaxies. These dwarf galaxies then merge over billions of years, building progressively larger galaxies. By the time the universe reaches its current age, massive dark matter halos have assembled, supporting giant galaxies like our Milky Way. But this hierarchical assembly takes time. Cosmological simulations show that truly massive dark matter halos capable of supporting Milky Way-sized galaxies shouldn't exist until at least a few billion years after the Big Bang. At 500 million years, only smaller halos should have formed. Yet, the 300 mysterious objects appear to be large, mature galaxies. If confirmed, they sit inside dark matter halos that shouldn't have had time to grow. This creates a serious problem for our understanding of structure formation. Claudia Lagos, a cosmology researcher studying these early galaxies, put it bluntly, having extremely massive galaxies so early in cosmic history poses significant challenges to our standard model. The Lambda CDM framework predicts specific growth rates for dark matter structure. These galaxies exceed those predictions. Several explanations have been proposed. Maybe dark matter clumped faster in certain regions due to random density fluctuations. Perhaps some exotic physics during the earliest moments after the Big Bang created pre-existing large-scale structure. Or possibly dark matter isn't purely cold, containing a component that behaves differently than expected. Another possibility is more radical. What if these objects aren't galaxies at all? Some astronomers suggest they could be massive black holes, surrounded by accretion disks that mimic the appearance of galaxies. Black holes can form faster than dark matter halos. A sufficiently massive black hole, feeding on surrounding gas, could produce the luminosity we're seeing, without requiring a full dark matter halo structure. But even that explanation has issues. How do such massive black holes form so quick? The standard path to supermassive black holes requires millions of years of growth. These objects would need to bypass several stages of black hole evolution. The invisible scaffolding that should support these galaxies simply wasn't ready yet. Either the scaffolding formed faster than physics predicts, or these objects don't need scaffolding the way we think they do. Our home galaxy, the Milky Way, is an ancient cosmic city. It contains roughly 200 billion stars, measures about 100,000 light years across, and has been forming stars for over 13 billion years. The galaxy we live in represents the culmination of eons of cosmic evolution. Now, imagine finding something similar when the universe was barely out of diapers. The Milky Way's story began soon after the cosmic dark ages ended. Small proto-galaxies formed first, each containing perhaps a few million stars. Over billions of years, these smaller systems collided and merged. Each merger added more stars and gas, gradually building the massive spiral structure we see today. The process was slow and steady. Our galaxy's stellar disk took several billion years to settle into its current shape. The spiral arms formed relatively recently, in cosmic terms, probably within the last few billion years. The central bulge, packed with older red stars, represents some of the earliest stellar populations. Even that ancient core took time to assemble. Current estimates suggest the Milky Way gained most of its mass between 8 and 10 billion years ago. Star formation peaked during that era, then gradually declined to the modest rate we observe today. The galaxy's growth was methodical, following the timelines predicted by cosmological models. Now look at the 300 early galaxies. Some appear to contain stellar masses approaching or even matching the Milky Way's total. That represents 10 to 100 billion solar masses worth of stars. But they achieved this in only a few hundred million years, perhaps less. They accomplished in a fraction of a billion years what took our galaxy over 10 billion years to build. The comparison reveals just how abnormal these objects are. Imagine if a human infant grew from newborn to full adult size in 1 week. That's roughly the proportional time difference we're talking about. These galaxies underwent compressed evolution at impossible speed. Their structure also differs from modern galaxies. Many early galaxies observed by Webb show flattened disk shapes or irregular tube-like structures. They lack the organized spiral arms or elliptical symmetry common in mature galaxies. They look chaotic, like construction zones rather than finished cities. The Milky Way benefits from over 13 billion years of chemical enrichment. Each generation of stars has added heavier elements to the gas supply, making subsequent stellar populations more complex. Our Sun, for example, is a third-generation star containing elements forged in earlier stars. This enrichment happens gradually over cosmic time. These early galaxies had minimal enrichment. They formed from nearly pure hydrogen and helium. Yet somehow, they built galaxy-scale stellar populations from this pristine gas. The efficiency required exceeds anything we observe in the modern universe. Think about the resources involved. Our galaxy consumed vast amounts of gas over billions of years to build its stellar population. It also lost enormous amounts of gas to stellar winds and supernova explosions. The net efficiency is relatively low. Much of the available gas never became stars. For the 300 early objects to reach comparable sizes so quickly, they must have converted gas to stars with incredible efficiency. Either they retain gas better, avoiding losses to feedback, or they somehow funneled gas inward faster than normal. Comparing them to the Milky Way highlights their impossible nature. They're like cosmic time travelers, exhibiting mature characteristics before they had time to develop them. Let's put the timeline problem in perspective. The universe is 13.8 billion years old. Earth formed about 4.5 billion years ago. Complex life emerged roughly 600 million years ago. Modern humans appeared around 300,000 years ago. 500 million years sounds like forever, but in cosmic terms, it's barely a moment. 500 million years after the Big Bang, the universe was 3.6% of its current age. To understand how young that is, imagine if Earth's entire 4.5 billion year history was compressed into one calendar year. 500 million years would be equivalent to just 40 days. We're talking about cosmic January here. During those first 500 million years, a lot had to happen. The cosmic dark ages had to end. The first stars had to form. Those stars had to live out their lives and explode. Their debris had to enrich the surrounding gas. Second and third generation stars had to form from that enriched material. Gas clouds had to collapse and merge. Star clusters had to gravitationally bind together, all of this within what amounts to cosmic infancy. Current models suggest the first stars ignited around 100 million years after the Big Bang. These primordial suns were massive, burning hot and bright, but dying within just a few million years. Their explosions seeded space with the first heavy elements. Second-generation stars began forming around 200 million years after the Big Bang. The earliest confirmed galaxies before James Webb's discoveries existed around 380 million years after the Big Bang. These were small systems containing perhaps 10 million to 100 million stars. They represented the expected early stage of galaxy formation, small building blocks that would later merge into larger structures. But the 300 mysterious objects appear to exist between 500 and 700 million years post-Big Bang. That's only 200 to 400 million years after the first stars formed. In that brief window, they somehow assembled stellar populations comparable to our modern Milky Way. Consider what this timeline requires. Stars need time to form. A typical star-forming region in our galaxy produces stars over a few million years. But you need multiple star-forming regions operating simultaneously to build billions of stars. You need gas clouds to collapse, fragment, and ignite in coordinated waves across the entire galaxy. Then there's the merger timeline. If these large galaxies form through mergers of smaller proto-galaxies, those smaller systems had to exist first. Each dwarf galaxy needs tens of millions of years to assemble. Then the mergers themselves take time, typically 100 million to 500 million years, depending on the masses and velocities involved. Cramming all these processes into 500 million years feels like trying to write a novel in an hour. You might produce something, but it won't be polished or comprehensive. Yet, these early galaxies don't look like rough drafts. They contain massive stellar populations, suggesting mature, established systems. Joel Leisha, an astrophysicist studying these objects, described them as bananas. His team expected to find small blue baby galaxies in the early universe. Instead, they found red mature systems that had apparently jumped ahead several development stages. Out of the 300 dropout candidates, over 240 fall into the extremely red object category. This isn't a minor detail, it's a major clue that something unusual happened in these systems. The extreme redness suggests processes beyond normal galaxy evolution. The technical definition uses magnitude differences. Magnitudes measure brightness on a logarithmic scale, where each step represents about 2.5 times more light. An extremely red object shows more than 2 magnitudes difference between 2 specific infrared filters. That translates to being over 6 times brighter at longer wavelengths compared to shorter ones. Why does this level of redness matter? Normal galaxies show color gradients, but not this extreme. Even old red galaxies in the nearby universe don't approach this level of red excess. The extremely red objects are so red they stand out as statistical outliers. Several factors could contribute to their appearance. The most obvious is redshift. As we discussed, cosmic expansion stretches light to longer wavelengths. The farther away an object, the more its light shifts toward the red. For galaxies at very high redshift, this effect is dramatic, but redshift alone doesn't fully explain the extreme nature. Theoretical models that include redshift predict certain color ranges for early galaxies. Many of these 300 objects exceed those predictions. They're redder than they should be, even accounting for their distance. Dust is the next suspect. Interstellar dust preferentially absorbs blue light while allowing red light to pass through. This is why sunsets appear red. Dust particles scatter shorter blue wavelengths, while longer red wavelengths travel relatively unimpeded. If these early galaxies contain substantial dust, it would make them appear redder. But as mentioned earlier, dust requires heavy elements. Those elements come from stellar evolution and supernovae. Building up significant dust in the first few 100 million years of cosmic history requires exceptionally rapid stellar cycling. Stars must form, age, and die quickly enough to produce dust in meaningful quantities. One possibility is that the first stars, being extremely massive, lived very short lives and produced disproportionate amounts of heavy elements. If enough of these primordial supergiants exploded early, they could enrich the local environment with dust-forming elements within 100 million years or less. Another factor is stellar population age. When a burst of star formation occurs, the galaxy initially glows blue from massive young stars. As those stars age and die, the remaining population shifts towards smaller, longer-lived red stars. After a few 100 million years without new star formation, a galaxy can become quite red. This scenario implies the extremely red objects experienced intense star formation bursts, followed by quiescence. They built up their stellar populations quickly, then stopped forming stars. That would make them red without requiring extreme dust content. Some astronomers call these sleeping beauty galaxies, systems that formed early and then went dormant. The challenge is explaining why they would stop forming stars. Modern galaxies stop star formation when they run out of gas, or when feedback from stars and black holes heats or expels remaining gas. But these early galaxies existed in a universe still filled with pristine hydrogen. Gas was abundant. What shut them down? The mid-infrared instrument on Webb provides additional insight into 37 of the extremely red objects. These observations penetrate dust better than near-infrared, allowing astronomers to see what's happening inside these systems. The data confirms many are legitimately distant and bright. The extreme redness isn't just a measurement quirk. It represents real physical properties that challenge our understanding. Determining an object's distance and age in astronomy requires more than just taking a picture. Astronomers need to analyze how bright the object appears at many different wavelengths. This rainbow of brightness measurements is called the spectral energy distribution, or SED. It's like a fingerprint that reveals hidden properties. Here's how it works. Different types of objects emit light in characteristic patterns. Hot, young stars pump out enormous amounts of ultraviolet and blue light. Cool, old stars produce mainly red and infrared light. Gas clouds heated by star formation emit at specific wavelengths. Dust absorbs short wavelengths and re-radiates longer ones. By measuring brightness across many wavelengths, astronomers can determine what's producing the light. The research team measured the spectral energy distribution for each of the 300 candidates. They used data from multiple Webb instruments covering different parts of the infrared spectrum. They also incorporated data from other telescopes when available, building a comprehensive picture of each object's brightness pattern. Then comes the analysis phase. Astronomers compare the observed spectral energy distribution to theoretical models. These models predict what galaxies at different distances and with different properties should look like. By finding the model that best matches the observations, researchers can estimate the galaxy's redshift, stellar mass, age, and other characteristics. The ST fitting for the 300 objects revealed surprising results. About 2/3 of them appeared to be closer than initially thought, at redshifts between 1 and 4. That places them around 2 billion to 12 billion years in the past. Still ancient by human standards, but not impossibly early in cosmic terms. These closer objects are interesting, but don't challenge cosmology. The remaining third, however, showed spectral energy distributions consistent with very high redshifts above 7 or even reaching 10 and beyond. These objects, if the estimates are correct, existed less than 700 million years after the Big Bang. They're the ones causing headaches. Their SEDs suggest mature stellar populations. The light patterns match what you'd expect from galaxies containing billions of stars with a mix of ages. Some stars appear to be several hundred million years old already. That's impossible if the galaxy formed just a few hundred million years after the Big Bang. It implies star formation began even earlier, perhaps within the first 200 million years. The stellar masses derived from SED fitting also raise eyebrows. Several objects show masses between 10 billion and 100 billion solar masses. That's enormous for such an early epoch. Building that much stellar mass requires converting vast amounts of gas into stars at rates exceeding anything observed in the modern universe. There's uncertainty, though. SED fitting isn't perfect. The method relies on theoretical models that might not fully capture the complexity of real galaxies. If these early systems evolved differently than modern galaxies, the models might give incorrect results. The derived ages and masses could be overestimated. That's why astronomers emphasize these are candidate galaxies. The spectral energy distribution analysis provides strong evidence, but it's not definitive proof. The next step is spectroscopy, which provides far more precise measurements. Spectroscopy spreads light into its component wavelengths, revealing absorption and emission lines from specific elements. These lines have known rest wavelengths. By measuring how much they've shifted, astronomers can determine the exact redshift with high precision. Spectroscopy also reveals chemical composition, temperature, density, and other properties. Until spectroscopic observations confirm the distances and properties, some uncertainty remains. But the spectral energy distributions already tell a compelling story. These objects, at least some of them, are extraordinarily massive and formed extraordinarily early. They're pushing the boundaries of what the infant universe should be capable of achieving. What if the 300 mysterious objects aren't galaxies at all? This question keeps some astronomers awake at night, because if there's something else entirely, it could explain their impossible properties without breaking the laws of physics. The leading alternative is both fascinating and unsettling. They might be black hole stars. Black hole stars are theoretical objects that shouldn't exist anymore. They're hypothesized to have formed in the very early universe under conditions that no longer occur. Picture this: a massive star begins to collapse. Normally, it would either explode as a supernova or collapse into a neutron star or black hole. But in the primordial universe, with its unique conditions, something different might happen. The star's core collapses into a black hole as expected, but instead of consuming the entire star, the black hole becomes trapped inside it. The black hole sits at the center, feeding on infalling material, while the outer layers of the star remain intact. The energy released by matter falling into the black hole actually prevents further collapse, stabilizing the structure. The result is a bizarre hybrid object. It looks like a star from the outside, glowing brightly, but it's powered by a black hole at its core, rather than nuclear fusion. These black hole stars could grow enormous, potentially thousands of times larger than normal stars, and they could shine incredibly brightly, mimicking the appearance of entire galaxies. This theory gained attention when astronomers discovered strange objects in Webb images that don't quite behave like galaxies. They're compact, extremely luminous, and very red. Some have been nicknamed little red dots. Their properties don't match expectations for either galaxies or quasar. Black hole stars could fit the observations. If the 300 candidates are actually black hole stars rather than galaxies, it solves several problems. Black holes can form faster than galaxies. They don't require extensive dark matter halo. They don't need hundreds of millions of years of gradual star formation. A single black hole star forming within just a few million years could produce the luminosity we're seeing. The extreme brightness also makes sense. Matter falling into a black hole converts mass to energy with incredible efficiency, far exceeding nuclear fusion. Even a relatively small black hole, feeding rapidly, could outshine billions of normal stars. If dozens or hundreds of black hole stars existed in the same region, their combined light would appear like a bright galaxy. But there are issues with this interpretation. Black hole stars, if they existed, should have been unstable. Most theoretical models predict they would collapse completely or explode within a few million years. Finding hundreds of them all at once seems unlikely unless they form continuously over longer periods. Also, spectral energy distribution analysis suggests extended structures rather than point sources. Galaxies have size, with light coming from distributed stellar populations. Black hole stars should appear more compact. Some of the 300 objects show hints of spatial extent that doesn't fit the point source model. Another problem is chemistry. Galaxies should show spectral signatures of stars, gas, and dust. Black hole stars would show different signatures related to accretion and extreme energies. Preliminary observations favor the galaxy interpretation, but more data is needed. Erica Nelson, one of the astronomers studying these objects, acknowledged the possibility. She noted that if these things turn out to be a different kind of weird object, like faint quasars, or something else, that would be just as interesting as finding impossible galaxies. The truth probably lies somewhere in the middle. Some of the 300 objects are likely genuine early galaxies. Others might be misidentified quasars or active galactic nuclei. A few could be black hole stars, if those exotic objects actually existed. Separating one from another requires detailed spectroscopic observations. But the fact that astronomers are seriously considering such exotic alternatives shows how unexpected these discoveries are. The early universe was shrouded in an opaque fog. This wasn't water vapor or dust. It was neutral hydrogen gas, filling all of space, absorbing and scattering light. Any galaxy trying to shine through this fog faced an impossible barrier. Photons couldn't travel more than a short distance before a hydrogen atom absorbed them. Yet somehow, light from these 300 objects reached us across 13 billion years. Understanding this barrier requires knowing what neutral hydrogen does to light. A hydrogen atom consists of one proton and one electron. When the electron orbits close to the nucleus, the atom is in its ground state. If a photon with exactly the right energy hits this atom, the electron absorbs the photon and jumps to a higher energy level. The photon is destroyed in the process. The key phrase is exactly the right energy. Hydrogen atoms absorb ultraviolet light at very specific wavelengths. The most important absorption happens at the Lyman alpha line, about 121 nanometers. Even more critically, hydrogen absorbs all ultraviolet light shorter than 91 nanometers, the Lyman limit we discussed earlier. In the early universe, space was filled with neutral hydrogen atoms in their ground state. Any ultraviolet photon traveling through this fog would be absorbed almost immediately. The average distance a photon could travel, called the mean free path, was incredibly short. Some calculations suggest a photon could travel only a few hundred light-years before being absorbed. For comparison, the nearest galaxy to our Milky Way is over 2 million light-years away. A photon needing to cross intergalactic space would be absorbed thousands of times over. The universe was effectively opaque to ultraviolet light. Hot young stars produce enormous amounts of ultraviolet radiation. That's their primary output. If all that UV light gets absorbed immediately by surrounding hydrogen, the stars remain invisible to distant observers. Any galaxy in the early universe would be cloaked by this cosmic fog, impossible to see from outside its local neighborhood. The only way light escapes is if the hydrogen gets ionized. Ionized hydrogen has lost its electron. Without an electron, it can't absorb photons the same way. Ionized hydrogen is essentially transparent, but ionizing hydrogen throughout the universe requires enormous amounts of energy. This process is called reionization. It began when the first stars and galaxies formed, producing enough UV radiation to ionize bubbles of hydrogen around them. Gradually, these ionized bubbles expanded and merged. Eventually, after several 100 million years, most of the hydrogen in the universe had been reionized. The fog lifted, light could travel freely again. Current estimates suggest reionization was substantially complete by about 1 billion years after the Big Bang, though it may have started earlier. The 300 mysterious galaxies existed during or possibly before reionization finished. That means they were shining into a universe still partially filled with neutral hydrogen fog. Some of their light should have been absorbed. Yet, we detect them clearly with James Webb. Either they formed in regions where reionization happened unusually early, creating clear pathways for light to escape, or they were so luminous that even with substantial absorption, they remained visible. Their brightness might itself have contributed to reionization. If these 300 objects were as luminous as they appear, they pumped enormous amounts of UV radiation into their surroundings. That radiation would ionize nearby hydrogen, carving out transparent zones. If enough such galaxies existed, they collectively might have driven reionization faster than models predict. But that creates a circular problem. We think they're visible because reionization happened, but reionization might have happened because they exist. Which came first? The hydrogen fog should have trapped their light. The fact that we see them at all suggests something unusual about either these objects or the state of the universe at that time. The Hubble Space Telescope operated for over 3 decades, capturing some of the most iconic images in astronomy. It peered deep into the universe, revealing galaxies billions of light-years away. It studied the cosmic dawn and found early galaxies forming hundreds of millions of years after the Big Bang. Yet, Hubble never saw the 300 mysterious objects James Webb discovered. Why did the most powerful telescope of its generation miss them entirely? The answer lies in wavelength. Hubble primarily observes ultraviolet, visible, and near-infrared light. Its interns cover wavelengths from about 20 nanometers in the ultraviolet to 1,1600 nanometers in the near-infrared. This range is perfect for studying nearby galaxies and moderately distant objects, but extremely distant galaxies have their light severely redshifted. Light that left them as ultraviolet or blue visible light gets stretched by cosmic expansion until it arrives as infrared radiation. For galaxies at redshifts above 7th, much of their light shifts beyond Hubble's detection range. James Webb was specifically designed to overcome this limitation. Its instruments cover wavelengths from 600 nanometers all the way to 28,000 nanometers. That's deep into the mid-infrared. Webb can see light that's been stretched far beyond Hubble's capabilities. Think of it like tuning a radio. Hubble was tuned to one set of frequencies. Webb is tuned to different, longer frequencies. The same objects transmit on both frequencies, but the signal is stronger at the wavelength each telescope is designed to detect. For extremely distant galaxies, Webb's infrared sensitivity is essential. Hubble did observe some of the same regions of sky where Webb found the 300 objects. The Cosmic Evolution Early Release Science Survey, which provided much of the data for the discovery, focused on an area Hubble had previously studied, but Hubble's images showed either nothing or extremely faint smudges, where Webb revealed bright red galaxies. This isn't a failure of Hubble, it's a limitation of physics. You can't detect light at wavelength your instruments aren't sensitive to. No amount of exposure time or clever processing could make Hubble see what Webb sees. The photons arriving from these distant galaxies simply fall outside Hubble's range. Webb also has another advantage: size. Its primary mirror measures 21 feet across, compared to Hubble's 8-foot mirror. Larger mirrors collect more light, allowing detection of fainter objects. Webb is about 6 times better at collecting light than Hubble. This sensitivity boost makes an enormous difference when observing extremely faint distant galaxies. The combination of infrared sensitivity and large mirror size allows Webb to see objects that were essentially invisible to Hubble. The 300 candidates were hidden in plain sight, broadcasting their presence at wavelengths Hubble couldn't detect. Some astronomers had predicted this would happen. Before Webb launched, theoretical models suggested numerous distant galaxies might exist beyond Hubble's detection limit, but the predictions underestimated how many and how bright these galaxies would be. Webb found more candidates and brighter ones than most models anticipated. Interestingly, Hubble did detect a few very distant early galaxies. It found some objects at redshifts around 7 to 8, but these were small, faint systems containing much less stellar mass than the 300 Webb discovered. They fit expectations. They were the baby galaxies astronomers expected to find. Webb's discoveries represent a different population. These are larger, brighter, and more mature than anything Hubble could see. They push into mass ranges that shouldn't exist so early. Hubble gave us a glimpse of the cosmic dawn. Webb is revealing that dawn was far brighter and more active than we imagined. The fact that Hubble missed them isn't surprising in retrospect. What's surprising is that they exist at all. Imagine trying to build a skyscraper but having access to only enough steel and concrete for a small house. That's essentially the problem these early galaxies present. The amount of matter available in the infant universe was limited, yet some of these 300 objects appear to contain stellar masses equivalent to tens or even hundreds of billions of suns. Where did all that mass come from? After the Big Bang, the universe consisted mostly of hydrogen and helium gas. About 73% was hydrogen, 25% helium, and tiny traces of lithium. Dark matter made up about 84% of total matter, but dark matter can't form stars. Only the ordinary matter could collapse into stellar objects. This gas was spread relatively thinly across space. The average density of matter in the universe was incredibly low, though it varied from place to place due to quantum fluctuations. Denser regions would eventually become galaxies. But even in these denser regions, gathering enough gas to build a massive galaxy takes time. Modern large galaxies, like the Milky Way, contain about 100 billion to 400 billion solar masses of stars. But they didn't acquire this mass all at once. They accumulated it over billions of years through continuous star formation, and by merging with smaller galaxies. Each merger added more mass. The process was gradual. For the 300 early candidates to possess comparable masses within just 500 million years, they needed to gather material at extraordinary rates. Gas from a large volume of space had to funnel into relatively small regions. The inflow rate must have been 10 to 20 times higher than in modern galaxies. Dark matter halos help facilitate this process. Their gravity pulls ordinary matter inward. But as we discussed, sufficiently massive dark matter halos shouldn't have formed yet at such early times. The halos that did exist were smaller, capable of supporting only dwarf galaxies. One possibility is that these objects formed in rare, extremely dense regions where matter concentration was unusually high. Statistical fluctuations in the initial density field mean some regions were denser than average. If a galaxy formed in one of these rare peaks, it could access more gas than typical. But this explanation only goes so far. Even the densest regions in standard cosmological models don't provide enough excess matter to explain these masses at such early times. You'd need density enhancements exceeding what random fluctuations typically produce. Another factor is gas accretion efficiency. Modern galaxies are wasteful. Much of the gas that falls into a dark matter halo never becomes stars. Feedback from stellar winds, supernova explosions, and active black holes heats the gas or blows it out of the galaxy entirely. Only a small fraction of available gas actually forms stars. If the early galaxies had higher efficiency, converting a larger percentage of inflowing gas into stars, they could build mass faster. Perhaps feedback was less effective in the early universe. The gas was denser and more pristine, possibly allowing more efficient star formation before feedback kicked in. Rapid mergers could also contribute. If multiple proto-galaxies formed close together and quickly merged, their combined mass would create a larger system. Instead of one galaxy slowly growing, several small ones join forces early. This requires special circumstances, but could happen in the densest regions. There's also the possibility that some of these objects aren't as massive as they appear, if they're actually quasars or black hole-powered systems. The extreme luminosity might mislead the mass estimate. A bright quasar could mimic the appearance of a galaxy containing billions of stars, while actually being a much smaller system. But if even a fraction of the 300 candidates are genuinely massive early galaxies, the mass mystery remains. The universe somehow concentrated billions of solar masses worth of gas into small regions and converted much of it into stars within an impossibly short time. The logistics don't add up using standard physics. Something about the early universe's mass distribution, or the efficiency of galaxy formation, must differ from what our models assume. Determining how far away something sits in the universe sounds straightforward until you actually try to do it. There are no cosmic mile markers, no distance signs floating in space. Everything astronomers know about distances comes from analyzing light, and for the 300 mysterious objects, getting those distances right is absolutely critical. Redshift is the key measurement. As space expands, it stretches light traveling through it. The amount of stretching directly relates to how much the universe has expanded since the light was emitted. More expansion means more stretching. More stretching means higher redshift. Higher redshift means looking farther back in time. Astronomers express redshift as a number called ZA. A galaxy at redshift 0 is right here, right now. A galaxy at redshift 1 existed when the universe was about half its current size. At redshift 7, the universe was 1/8 its present size. At redshift 10, it was 1/11 its size. These fractions tell us how much expansion occurred between then and now. The 300 candidates show a wide range of estimated redshifts. Initial analysis using the dropout technique suggested many might sit at redshifts above 7, meaning they existed less than 800 million years after the Big Bang, but dropout estimates are approximate. They provide ballpark figures, not precise measurement. The spectral energy distribution fitting refined these estimates. By comparing observed brightness across multiple wavelengths to theoretical models, astronomers narrowed down the likely redshift ranges. About 2/3 of the objects appear to sit at redshifts between 1 and 4, still distant, but not impossibly early. The remaining 100 or so candidates, however, showed spectral energy distributions consistent with redshifts above 7. Some potentially reach redshifts of 10 or higher. If correct, these objects existed when the universe was between 3 and 5% of its current age. They're witnessing cosmic infancy. But there's uncertainty in these measurements. Spectral energy distribution fitting relies on models that might not perfectly represent reality. If these early galaxies had unusual properties not included in standard models, the derived redshifts could be wrong. An object thought to be at redshift 10 might actually sit at redshift 5 or 6. That's where spectroscopy becomes essential. Unlike broad filter imaging, Spectroscopy spreads light into a detailed rainbow. It reveals absorption and emission lines from specific atoms and molecules. Each element produces lines at known wavelengths when at rest. By measuring how much those lines have shifted, astronomers determine the exact redshift with far greater precision. For example, hydrogen produces a strong emission line at 656 nanometers when at rest. This is called H-alpha. If a galaxy's H-alpha line appears at 1312 nanometers, exactly double the rest wavelength, the redshift is 1. The line has been stretched by a factor of 2, meaning the universe has expanded by a factor of 2 since the light was emitted. Spectroscopy also reveals what's producing the light. Stars have characteristic spectral signatures different from gas clouds or active galactic nuclei. By examining the detailed spectrum, astronomers can confirm whether an object is truly a galaxy or something else masquerading as one. The challenge is that spectroscopy requires more observation time than imaging. You need to collect light for hours or even days to build up a strong enough spectrum for analysis. With hundreds of candidates to follow up, that represents a massive commitment of telescope time. Priority goes to the brightest and most interesting targets. Astronomers are currently planning spectroscope observations of dozens of the candidates. These observations will confirm distances, reveal chemical compositions, and determine stellar population. Within the next year or two, we'll know for certain which of these objects are genuinely ancient and which are imposters. Until then, the redshift measurements remain provisional, but even the provisional estimates are shocking enough to demand attention. Stars don't form instantly. The process follows specific physical rules with speed limits built in, yet the 300 early galaxies appear to have violated those limits, creating stars faster than physics should allow. Understanding why requires looking at what normally regulates star formation. In modern galaxies, star formation happens in cold, dense molecular clouds. These clouds contain mostly hydrogen molecules with temperatures around -440 degrees F. Gravity slowly compresses the densest parts of these clouds. As material falls inward, it heats up. When the center reaches about 18 million degrees, nuclear fusion ignites and a star is born. This collapse process typically takes about 10 million years from initial clump to newborn star. That might sound fast, but it imposes limits on how quickly a galaxy can build stellar populations. If each star takes 10 million years to form, and you're forming them one at a time, building billions of stars takes billions of years. Real galaxies form many stars simultaneously in different regions. A single molecular cloud might spawn hundreds or thousands of stars over a few million years. Multiple clouds across the galaxy form stars at the same time. This parallelization speeds things up considerably, but there are still constraints. The main one is feedback. Massive young stars produce intense radiation that heats surrounding gas. This heat increases gas pressure, which opposes gravitational collapse. The heated gas becomes harder to compress into new stars. Massive stars also drive powerful stellar winds that blow gas away from star-forming regions. When massive stars die as supernovas, the explosions inject enormous energy into the surrounding environment. This energy heats, disperses, and ionizes nearby gas. For a while after a supernova, star formation in that region effectively shuts down. The gas needs time to cool and settle before forming stars again. These feedback mechanisms keep star formation rates in check. Even the most active starburst galaxies in the modern universe rarely exceed 100 solar masses per year. Most typical galaxies form stars at rates between 1 and 10 solar masses annually. The feedback acts like a thermostat, preventing runaway star formation. Now consider what the early candidates accomplished. If they truly contain 50 billion to 100 billion solar masses of stars, and they built these populations in 500 million years, the average star formation rate must have been 100 to 200 solar masses per year, sustained for 500 million years. That's already at the extreme end of what we observe today. But remember, these rates need to account for stellar deaths too. Massive stars live only a few million years. They die and stop contributing to the stellar mass. To maintain a growing stellar population, you need to form stars faster than they die. When you factor in stellar death rates, the required star formation rates jump even higher. Some estimates suggest these galaxies needed to sustain rates of 300 to 500 solar masses per year during their peak growth periods. That's 3 to 5 times higher than the most extreme starbursts we observe anywhere in the modern universe. How do you achieve such rates without feedback shutting everything down? One possibility is that feedback was less effective in the early universe. The gas was denser and more gravitationally bound. It might have resisted being blown away despite intense stellar winds and supernovas. Another idea involves star formation efficiency. Maybe the first stellar populations formed in unusually efficient bursts where large percentages of available gas converted to stars before feedback kicked in. Instead of the typical few percent efficiency seen today, early galaxies might have achieved 10 or 20% efficiency. There's also the possibility of sustained inflow. If gas continuously streamed into these galaxies from their surroundings, star formation could continue even as feedback expelled material. The expelled gas gets replaced by fresh inflowing gas. This requires special geometric configurations or density distributions not common in the modern universe. Some astronomers suggest the star formation might not have been steady. Instead of constant rates, these galaxies experienced multiple intense bursts separated by quiet periods. Each burst converted enormous amounts of gas to stars over just a few million years, then shut down. Multiple bursts could build up large stellar populations without requiring sustained extreme rates. But even burst scenarios struggle to match the observations. The bursts need to be incredibly intense and occur frequently enough to build the required stellar masses. Whatever mechanism drove star formation in these early galaxies operated beyond our current understanding. The universe underwent one of its most dramatic transformations between 400 million and 1 billion years after the Big Bang. During this era, called the Epoch of Reionization, neutral hydrogen filling all of space became ionized again. The cosmic fog lifted. Light could travel freely for the first time since the Dark Ages began. The 300 galaxies should have been part of this process. Instead, they might have finished before it even started. Understanding reionization requires knowing what needed to change. After recombination, 380,000 years after the Big Bang, hydrogen existed as neutral atoms with electrons bound to protons. This neutral hydrogen absorbed ultraviolet light, making the universe opaque. For reionization to occur, something needed to strip electrons away from hydrogen atoms throughout all of space. Says something was ultraviolet radiation from the first stars and galaxies. Hot, young stars produce copious UV photons, energetic enough to ionize hydrogen. Each UV photon can knock an electron off a hydrogen atom. As more stars formed, more UV radiation flooded the universe. Gradually, bubbles of ionized hydrogen expanded around each galaxy. These ionization bubbles grew and merged. Eventually, they overlapped, filling most of space with ionized hydrogen. The transformation wasn't instantaneous. It took several 100 million years for the universe to transition from mostly neutral to mostly ionized. Current estimates suggest reionization was substantially complete by about 1 billion years after the Big Bang. The 300 mysterious galaxies existed during or before this transition. If they formed at 500 to 700 million years post-Big Bang, they were shining when the universe was still significantly neutral. The light had to punch through the remaining hydrogen fog to reach us. But here's where things get interesting. If these objects were as bright and numerous as they appear, they should have contributed massively to reionization. 300 bright galaxies pumping out UV radiation would ionize enormous volumes of hydrogen. If similar populations existed across the entire sky, not just in the surveyed regions, thousands of such galaxies might have existed. Collectively, they could have driven reionization faster and earlier than current models predict. Some simulations suggest that if massive galaxies formed as early and as abundantly as Webb observations hint, reionization could have been substantially complete by 600 million years after the Big Bang. That's 400 million years earlier than standard estimate. Early reionization creates problems, though. We have observational constraints on when reionization occurred. Astronomers study distant quasars, whose light passed through the universe when it was partially neutral. The quasar light shows absorption features from neutral hydrogen, allowing researchers to map how much neutral hydrogen existed at different times. These observations suggest significant neutral hydrogen remained until at least 800 million years after the Big Bang. Reionization wasn't finished early. It proceeded more or less on the timescale standard models predict. If the 300 galaxies existed and were bright, why didn't they reionize the universe faster? One answer is that most of their UV radiation never escaped. Perhaps dust within the galaxies absorbed the UV photons before they could ionize surrounding hydrogen. Or maybe the galaxies were surrounded by especially dense neutral hydrogen that absorbed UV radiation in their immediate vicinity, preventing it from reaching intergalactic space. Another possibility is that these objects aren't as numerous as they seem. The surveyed area represents a tiny fraction of the sky. Maybe the researchers happened to observe an unusually dense region. If so, the actual number of such galaxies across the whole universe would be much lower, producing less UV radiation overall. Or perhaps their redshift estimates are wrong. If most of the candidates actually sit at lower redshifts, they existed later in cosmic history when reionization was already underway or complete. They wouldn't need to contribute to early reionization because they simply weren't there yet. The alternative is more radical. Maybe reionization did proceed faster than we think, but in an uneven way. Large regions became fully ionized early, while other regions remain neutral longer. The observational constraints come from specific lines of sight to distant quasars. Those sight lines might pass through regions that stayed neutral longer than average. Reionization is one of the least understood epochs in cosmic history. We have observational hints, but not complete data. The 300 galaxies add another puzzle piece, but it's not clear yet where this piece fits in the overall picture. Either they contributed to reionization in ways we don't fully understand, or they existed in a universe already more ionized than we realize. Every field of science has a foundational framework, a set of rules explaining how things work. In cosmology, that framework is called lambda CDM. It stood as our best explanation for cosmic evolution for decades. The 300 galaxies James Webb discovered might require rewriting parts of it. Understanding what's at stake requires knowing what lambda CDM actually says. Lambda refers to dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold dark matter, the invisible substance providing gravitational scaffolding for structure formation. Together with ordinary matter, radiation, and the laws of general relativity, these components create a model that explains most observations of the universe. Lambda CDM makes specific predictions about how structure forms over time. In the beginning, matter was distributed almost uniformly, with tiny density variations. These variations came from quantum fluctuations during inflation. Over time, gravity amplified the variations. Denser regions pulled in more matter, becoming denser still. The model predicts a bottom-up growth pattern. Small structures form first. Dwarf galaxies assemble within a few 100 million years after the Big Bang. These dwarfs merge over time, building progressively larger galaxies. Giant galaxies like the Milky Way don't fully assemble until several billion years have passed. The timeline is hierarchical and relatively slow. Lambda CDM also predicts how many galaxies of each mass should exist at different times. Early in cosmic history, you should find many small galaxies and very few large ones. As time progresses, the number of large galaxies increases through mergers. By calculating how structure grows under gravity, cosmologists can predict the mass distribution of galaxies at any epoch. These predictions have been tested extensively. Surveys of nearby galaxies match lambda CDM expectations well. Observations of the cosmic microwave background, the oldest light we can see, also agree with the model's predictions. For decades, lambda CDM has successfully explained observation after observation. But the 300 early galaxies challenge this success. If even a fraction of them are genuinely massive and genuinely ancient, they exist in numbers. Lambda CDM doesn't predict. The model says massive galaxies should be extremely rare, 500 million years after the Big Bang. Finding hundreds in a relatively small survey area suggests they're not rare at all. There are several possible resolutions. The simplest is that most of the candidates aren't actually at high redshift. If their distances were overestimated, they're not as early or as problematic as they appear. Follow-up spectroscopy might reveal that many sit at lower redshifts where lambda CDM comfortably accommodates. Another possibility is that lambda CDM is mostly correct, but missing some details. Maybe dark matter isn't entirely cold. Perhaps it has a warm component that speeds up structure formation in certain ways. Or maybe the initial density fluctuations from inflation were larger than we thought in rare regions, allowing faster galaxy growth there. A more significant change would involve the star formation physics. Lambda CDM focuses on dark matter and large-scale structure. It doesn't model the detailed processes of star formation within galaxies. If star formation was more efficient in the early universe than current models assume, galaxies could build stellar mass faster without violating the dark matter framework. The most radical resolution is that lambda CDM needs fundamental revision. Maybe dark matter behaves differently than we think. Perhaps dark energy was stronger or weaker in the early universe, or possibly general relativity itself needs modification to explain these observations. Most cosmologists aren't ready to abandon lambda CDM yet. The model has too many successes to discard based on one set of observations, but they're definitely concerned. If spectroscopy confirms that many of the 300 candidates are genuinely high redshift massive galaxies, lambda CDM will need significant adjustments. Joel Layer put it directly. Finding these objects challenges current ideas about how galaxies formed in the early universe. The emphasis on challenges is polite scientific speak, for this doesn't fit what we expected at all. The next few years will determine whether lambda CDM survives intact, requires modifications, or faces a crisis demanding new physics. The 300 galaxies are forcing cosmologists to confront uncomfortable questions about their most successful theory. What if the impossible galaxies had help from the universe's earliest moments? Some cosmologists are exploring a radical idea, maybe primordial black holes. Objects formed during the first seconds after the Big Bang seeded the growth of these massive galaxies. It sounds like science fiction, but the physics might actually work. Primordial black holes are different from the black holes we normally discuss. Regular black holes form when massive stars collapse. That process requires stars to exist first. Primordial black holes form differently. During the first fraction of a second after the Big Bang, density fluctuations in the expanding universe could have been strong enough to create black holes directly from compressed energy and matter. These primordial black holes could have any mass. Some might be tiny, weighing less than a mountain. Others could be enormous, containing thousands or millions of solar masses. Unlike stellar black holes that take millions of years to grow, primordial black holes would exist from the very beginning of cosmic time, already massive. Now imagine one of these primordial black holes sitting in a dense gas cloud during the cosmic dark ages. The black hole's gravity pulls gas inward. As gas spirals into the black hole, friction heats it to millions of degrees. The hot gas radiates enormous amounts of energy. This radiation heats and ionizes surrounding gas, affecting nearby star formation. The energy from the black hole could actually trigger star formation. Compression waves from the heated gas might cause distant cold gas to collapse into stars. At the same time, gas closer to the black hole gets dispersed, creating a complex pattern of enhanced and suppressed star formation. Primordial black holes could also act as gravitational anchors. Their mass helps pull matter into dense concentrations faster than dark matter alone. A million solar mass black holes sitting at the center of a proto-galaxy would significantly boost the rate at which gas falls inward. More gas means more stars forming over the same time period. This mechanism could explain how massive galaxies assembled so quickly. Instead of waiting for dark matter halos to slowly build up, these galaxies had primordial black holes jump-starting the process. The black holes provided both gravitational anchors and energy sources that accelerated galaxy formation. There's indirect evidence that supermassive black holes existed very early. Webb and other telescopes have found quasars, extremely bright objects powered by supermassive black holes at redshifts above 7. These black holes contain millions or billions of solar masses. Growing them from stellar masses in the available time is challenging. Primordial black holes offer an alternative origin. If primordial black holes seeded early galaxies, it could explain several puzzling features. The extreme brightness of some early objects makes sense if they contain actively feeding central black holes. The rapid mass assembly works if the black hole's gravity accelerated gas inflow. Even the unusual colors could result from black hole activity heating surrounding dust. But there are problems with this idea. We don't have direct evidence that primordial black holes exist. They're theoretically possible, but never confirmed. Detecting them is extremely difficult because they don't emit light unless they're actively feeding on matter. Most might be dark and invisible, drifting through space undetected. Also, primordial black holes should be extremely rare if they exist at all. Current constraints from various observations suggest that only a tiny fraction of dark matter could be in the form of primordial black holes. Having hundreds of early galaxies seeded by them requires either that primordial black holes are more common than we think, or that we got very lucky in where we pointed James Webb. Another issue is that black hole activity should produce specific observational signatures. Active feeding black holes create X-rays, strong emission lines, and jets. Some of the 300 candidates show hints of these features, but many don't. If primordial black holes seeded all of them, why don't all show black hole signature? The idea remains speculative, but it represents the kind of creative thinking astronomers are pursuing. When observations don't fit standard models, you explore alternatives. Primordial black holes might not be the answer, but investigating the possibility could reveal new insights about the early universe. Sometimes the most unlikely ideas turn out to be correct. Right now, astronomers are keeping all options on the table. Not all the mysterious early objects are blazing with star formation. Some apparently went dormant remarkably early, shutting down their stellar assembly lines. While the universe was still in its infancy, astronomers call them sleeping beauty galaxies, and they're almost as puzzling as the actively forming ones. A dormant galaxy contains stars, but isn't creating new ones. All its gas is either being consumed, expelled, or heated so much it can't collapse. The galaxy's stellar population ages quietly, without replacement. In the modern universe, dormant galaxies are common. Many massive elliptical galaxies stopped forming stars billions of years ago, but finding them in the early universe is shocking. The first sleeping beauty was discovered in data predating James Webb's 300 candidates. Astronomers found a galaxy that existed just 680 million years after the Big Bang and showed no signs of ongoing star formation. Its spectrum revealed old stars with ages suggesting they formed even earlier. The galaxy had built up its stellar population quickly, then inexplicably stopped. Since that initial discovery, more sleeping beauties have turned up. Some of the 300 candidates Webb found might be dormant rather than actively forming stars. Their extreme redness could indicate old stellar populations rather than dusty young ones. Distinguishing between these interpretations requires detailed spectroscopy. Why would a galaxy stop forming stars so early? In the modern universe, we understand several quenching mechanisms. A supermassive black hole at the galaxy's center can heat surrounding gas, preventing it from cooling and forming stars. Mergers between galaxies can disrupt gas supplies. Ram pressure from moving through intergalactic gas can strip a galaxy of its fuel, but these mechanisms shouldn't work effectively in the early universe. Supermassive black holes take time to grow. They probably weren't massive enough yet to heat and expel large amounts of gas. The intergalactic medium was thinner, making ram pressure stripping less effective. Mergers could disrupt gas temporarily, but shouldn't permanently quench star formation in such a gas-rich environment. There's also the timing problem. These galaxies apparently formed most of their stars within the first few 100 million years, then stopped. The rapid formation we've discussed makes sense if gas was available and collapsing efficiently. But what changed to suddenly halt the process? One idea involves feedback from the first generation of stars. If an intense burst of massive stars formed all at once, their combined supernovas could create a shockwave powerful enough to blow most remaining gas out of the galaxy. Without gas, star formations, but the galaxy would need to retain the gas it already converted to stars, while losing the rest. That's a delicate balance. Another possibility is environmental effects. Maybe these sleeping beauties formed in regions that became depleted of gas unusually quickly. Nearby galaxies or energetic events might have consumed or ionized the available hydrogen, starving these galaxies of new material. Some astronomers suggest the sleeping beauties aren't truly dormant, but just taking a break. They might go through cycles of active star formation followed by quiet periods. What we're seeing is a temporary pause. Given another few 100 million years, they might reignite star formation when fresh gas becomes available. The sleeping beauties also raise questions about how common they are. If a significant fraction of early galaxies went dormant quickly, it affects our understanding of how stellar mass accumulated over cosmic history. Mass locked up in dormant galaxies doesn't contribute to later star formation or galaxy growth. It represents a dead end in the evolutionary tree. Some of these objects show signs of possible rejuvenation in later observations. A galaxy dormant at redshift 8 might show renewed star formation by redshift 6. The sleep isn't necessarily permanent, but the fact that they could go dormant at all so early in cosmic history challenges our assumptions about how galaxy evolution proceeds. Finding these sleeping beauties wasn't expected. Neither was finding 300 extremely bright, actively forming galaxies. The early universe appears far more diverse than our models predicted. Some galaxies formed stars at impossible rates. Others somehow formed stars briefly and stopped. The variety suggests galaxy formation involved complex processes we don't fully understand. The sleeping beauties are teaching us that early galaxies didn't follow a single evolutionary path. Multiple formation mechanisms might have operated simultaneously, producing different outcomes. Among the 300 mysterious objects, 3 stand out as particularly impossible. Astronomers discovered these red monsters in a separate study, also using James Webb data. They're so massive and so early that they make the other candidates look almost reasonable by comparison. Each contains stellar populations rivaling the largest galaxies in the modern universe. Yet, they existed just 700 million years after the Big Bang. The 3 red monsters sit at redshifts around 7 to 8. That places them in the era when regionalization was still ongoing, when most galaxies should have been small and developed. Instead, these objects contain estimated stellar masses between 80 billion and 200 billion solar masses each. For comparison, the Milky Way contains roughly 100 and 150 billion solar masses of stars. Finding one such massive galaxy at that epoch would be surprising. Finding 3 in a relatively small survey suggests they might not be as rare as theory predicts. If the surveyed area contains 3, how many exist across the entire observable universe? Potentially thousands. What makes these red monsters especially problematic is their efficiency. Galaxies form stars from gas, but not all available gas becomes stars. Most modern galaxies convert only 10 to 20% of their gas mass into stars. The rest either never collapses or gets expelled by feedback. This low efficiency is why galaxy formation is slow. The 3 red monsters apparently converted gas to stars with extraordinary efficiency. Calculations suggest they turned 40 to 50% of available gas into stars. That's unprecedented. No galaxy in the modern universe achieves such high efficiency. These objects somehow bypass the feedback mechanisms that normally prevent efficient star formation. Ivor Labby, an astronomer studying these objects, described them as posing a tantalizing puzzle. Many processes in galaxy evolution introduce rate-limiting steps. Feedback heats gas, supernova explosions disperse material, black hole activity can shut down star formation. Yet, these red monsters evaded most hurdles and built up enormous stellar populations at breakneck speed. The term red monster comes from their extreme color. Like the other candidates, they glow deep red in infrared images. Their spectral energy distribution suggests they're dusty, mature systems with large populations of old stars. Some might even be partly dormant, having already gone through their most active star-forming phase. If these objects formed through the standard hierarchical process, they represent the merger of dozens or hundreds of smaller proto-galaxies. But there wasn't time for that many mergers. At 700 million years after the Big Bang, the universe barely had time for one or two major merger events per system. Building such massive galaxies would require continuous mergers happening faster than simulations predict. The alternative is that they formed through a more direct collapse process. Instead of gradually assembling from small pieces, they might have formed when massive gas clouds collapsed almost all at once. This top-down formation contradicts Lambda CDM's bottom-up predictions, but the observations seem to demand it. The three red monsters also raise questions about dark matter. To support such massive galaxies, they'd need to sit in extremely massive dark matter halos. These halos would need to contain at least 1 trillion solar masses of dark matter. Building such massive halos within 700 million years pushes the limits of what cold dark matter models allow. Some researchers wonder if we're seeing statistical flukes. Maybe these three galaxies formed in an unusually dense region where conditions favored rapid growth. The universe is large enough that rare events occasionally happen. Perhaps we're witnessing an extremely improbable configuration that shouldn't generalize to other regions. But finding three such objects in one survey seems like too many coincidences. If they were truly rare, 1 in a billion occurrences, we shouldn't have found any in the surveyed area. Finding three suggests they're uncommon, but not impossibly rare. And if they're not impossibly rare, cosmological models need to explain how they form. The red monsters push already strained theories to their breaking point. They're not just challenging details of galaxy formation models. They're questioning fundamental assumptions about how quickly massive structures can assemble in the early universe. These three objects might represent the most extreme examples yet found, but they probably aren't alone. The story we've told about the universe's earliest galaxies is changing. For decades, textbooks painted a picture of gradual growth, with small galaxies slowly merging into larger ones over billions of years. The first chapter of cosmic history described a universe emerging slowly from darkness, cautiously building its first structures. The 300 galaxies James Webb discovered are forcing us to rip out that chapter and start over. Here's what we thought we knew. After the cosmic dark ages ended, around 400 million years after the Big Bang, the first stars formed. These primordial stars were isolated giants scattered sparsely through space. Over the next few 100 million years, they began clustering into small proto-galaxies containing perhaps 10 million to 100 million stars each. These dwarf galaxies were the building blocks. They merged pairwise, combining their stellar population. Two dwarfs merge to make a slightly larger galaxy. That larger galaxy merges with another, growing incrementally. The process resembled construction, carefully assembling a structure piece by piece. By 1 billion years after the Big Bang, modest galaxies started appearing. Truly large galaxies wouldn't exist for several billion more years. This narrative fit observations beautifully. Hubble found small blue galaxies in the early universe, exactly as predicted. The cosmic microwave background showed tiny density fluctuations that would gradually grow into galaxies. Computer simulations confirmed that bottom-up assembly matched theoretical expectations. Everything made sense. Then James Webb started observing. The 300 candidates appeared far too bright and massive for their age. The Sleeping Beauty galaxies showed stellar populations that formed and shut down impossibly early. The three red monsters contained stellar masses that shouldn't exist for billions of years. The entire carefully constructed narrative began unraveling. The new picture emerging from Webb's data is more violent and chaotic. The early universe wasn't cautious, it was aggressive. Galaxies formed faster, grew larger, and evolved quicker than anyone predicted. Star formation rates exceeded modern extremes by factors of 5, or gas collapsed efficiently, despite processes that should have prevented it. This revised history has profound implications. If massive galaxies formed so early, they would have ionized the universe faster, changing the timeline of reionization. Their stars would have produced heavy elements sooner, enriching the early intergalactic medium. Supermassive black holes could have grown earlier and larger, explaining some of the extremely massive black holes found at high redshifts. The formation of large galaxies early in cosmic history also affects how we understand galaxy evolution overall. If some galaxies reached massive sizes quickly, their subsequent evolution differs from galaxies that grew gradually. They might have exhausted their gas supplies sooner, becoming dormant earlier, or they might have triggered different feedback processes that affected later star formation. Cosmologists are also reconsidering what the cosmic microwave background tells. The tiny fluctuations we observe in that ancient light led to predictions about structure, formation rates. If those predictions are wrong, maybe we're misinterpreting the fluctuations. Perhaps the early universe had additional physics at work that current models don't include. The rewritten first chapter also changes how we think about our own galaxy. The Milky Way formed gradually, over billions of years, but now we know that wasn't the only path. Some galaxies assembled rapidly in the early universe, then spent billions of years slowly evolving. The diversity of formation mechanisms is greater than we realized. This isn't just about fixing numbers in theoretical models. It's about fundamentally reconceiving what happened during the universe's infancy. The first billion years were apparently more dynamic, more efficient at building structure, and more capable of producing mature galaxies than we ever imagined. The revised chapter reads very differently from the old one. Instead of slow and steady, it's fast and furious, and we're still not sure we understand the plot. Right now, the 300 candidates exist in scientific limbo. They're tantalizing, puzzling, and potentially revolutionary, but they're not confirmed. The next phase of research will determine which candidates are genuinely ancient, massive galaxies, and which are imposters. That determination requires spectroscopy, and astronomers are already planning the observations. Spectroscopy doesn't just take pictures, it dissects light into its component wavelengths, revealing absorption and emission lines from atoms and molecules in the source. Each element produces lines at specific wavelengths. Hydrogen creates a series of lines called the Balmer series. Oxygen produces distinctive lines in the visible and infrared. Heavy elements like iron have complex patterns of lines. When light travels across cosmic distances, all these lines shift together by the same fact. By identifying the lines and measuring their shifted wavelengths, astronomers determine the exact redshift. This measurement is far more precise than photometric estimates from broadband imaging. Spectroscopy can pin down redshift to within a fraction of a percent. For the 300 candidates, spectroscopy will answer the most basic question: how far away are they really? If most turn out to have lower redshifts than estimated, they're not as early or as massive as they appear. They become interesting, but not paradigm-breaking. If many confirm high redshifts above 7, the crisis for cosmology intensifies. Spectroscopy also reveals what's producing the light. Stars have characteristic spectra dominated by absorption lines from elements in their atmosphere. Active galactic nuclei show strong emission lines from hot gas near supermassive black holes. Quasars have very different spectral signatures from normal galaxies. By examining the spectrum, astronomers can definitively determine whether an object is a galaxy, quasar, or something else. Chemical composition comes from spectroscopy too. The relative strengths of different spectral lines indicate which elements are present and in what quantities. Early galaxies should show low metallicity, meaning few heavy elements. They formed from nearly pure hydrogen and helium. If a supposed early galaxy shows high metallicity, it's probably not as ancient as it appears. Stellar population age estimates improve dramatically with spectroscopy. Absorption features from certain elements appear only in stars of specific ages. Young stars show strong hydrogen lines. Old stars show molecular absorption bands. By analyzing the full spectrum, astronomers can determine the mix of stellar ages within a galaxy and estimate when most stars formed. Webb is already conducting spectroscopy follow-up on selected targets. The brightest candidates get priority since they require less observation time. Each spectrum takes between 2 and 10 hours of telescope time, depending on the object's brightness. With hundreds of candidates, completing spectroscopy on all of them would take years. The first results are starting to appear. Some candidates have been confirmed at high redshift. Others turned out to be at lower redshifts, ruling them out as impossible early galaxies. A few showed spectral features suggesting they're quasars or other exotic objects rather than normal galaxies. The picture is becoming clearer, but remains incomplete. Future spectroscopy surveys will observe larger samples more efficiently. Webb will continue follow-up observations for years. Ground-based telescopes, like the extremely large telescope under construction in Chile, will add their capabilities. Together, these facilities will eventually spectroscopically confirm or reject most of the 300 candidates. The confirmed high redshift massive galaxies will become prime targets for even more detailed observations. Astronomers will want to study their spatial structure, measure their dynamics, search for supermassive black holes at their centers, and understand their star formation history. Each confirmed object becomes a laboratory for testing theories about early galaxy formation. Spectroscopy will also search for surprises. Some candidates might have unexpected properties that current models don't predict. Unusual chemical compositions could hint at exotic formation mechanisms. Strange kinematic signatures might reveal unseen companions or merger events. The detailed information from spectra often raises as many questions as it answers. Within 5 years, we'll have spectroscopic confirmation for most of the brightest candidates. That data will determine whether the 300 galaxies represent a genuine crisis for cosmology or a temporary anomaly explained by more careful analysis. The telescope time is allocated. The observations are being scheduled. Soon we'll know the truth. When observations clash with theory, scientists face a fundamental choice. Either the observations are wrong, or the theory needs revision. For the 300 early galaxies, we're fairly confident the observations are real. James Webb Space Telescope is working as designed. The photons it detected genuinely came from distant objects, which leaves the uncomfortable possibility that our theories need major changes, maybe even new physics. New physics is a phrase scientists use carefully. It doesn't mean throwing out everything we know. Einstein's relativity didn't invalidate Newton's laws of motion. It extended them to new regimes. Quantum mechanics didn't erase classical physics. It added new rules for atomic scales. New physics typically means discovering that our current understanding is incomplete, not entirely wrong. Several areas of physics might need revision to explain the early galaxies. The most obvious is star formation theory. Current models predict specific rates at which gas can collapse and form stars. These rates depend on gas properties, gravity, turbulence, magnetic fields, and feedback. Maybe some factor is missing from the models. Perhaps star formation worked differently when the universe was young and gas had different properties. If star formation efficiency was dramatically higher in the early universe, existing physics might explain it without requiring new laws. We just need to understand why conditions differed from what we assumed. That's not new physics. It's refining existing physics. Dark matter presents another possible avenue for new physics. We know dark matter exists through its gravitational effects, but we don't know what it is. Current models assume it's entirely cold, meaning the particles move slowly and clump efficiently. Maybe dark matter has properties we haven't discovered. Perhaps it interacts weakly with itself in ways that accelerate structure formation. that would constitute genuinely new physics. Some theorists are exploring modifications to gravity itself. What if general relativity isn't the complete story? Maybe gravity works slightly differently on large scales or at early times. Modifications to gravity could change how quickly structures form without invoking dark matter at all. Such modifications would represent major new physics. Another possibility involves dark energy. We know dark energy drives the accelerating expansion of the universe today. But was dark energy weaker or stronger in the past? If dark energy evolved over cosmic time in unexpected ways, it could affect structure formation rates. That would require new physics beyond the cosmological constant. Even more speculative ideas involve modifications to quantum mechanics or inflation theory. Perhaps quantum fluctuations during inflation were larger than we thought, seeding bigger initial density variations. Those larger seeds would grow into massive structures faster. Modifying inflation theory at this level ventures into very new physics territory. Here's the critical question: how much can we adjust existing theories before we have to admit we need genuinely new physics? If tweaking a few parameters or refining models of star formation efficiency solves the problem, that's not revolutionary. It's normal scientific progress. Theories always need refinement as new data arrives. But if no amount of parameter tweaking makes existing models match observations, we face a real crisis. That's when scientists seriously consider new physics. We're not there yet with the early galaxy. Many avenues remain to be explored within existing frameworks, but we're closer to that threshold than at any time in recent decades. The history of astronomy includes several cases where new observations forced genuinely new physics. The discovery of Neptune solved anomalies in Uranus's orbit without new physics. But anomalies in Mercury's orbit eventually required Einstein's general relativity, which was new physics. Dark matter and dark energy themselves represent read physics, added to explain observations that couldn't be fit with known matter alone. Perhaps the early galaxies will ultimately fit within lambda CDM, with some adjustment. Maybe they're pointing to gaps in our understanding that require new particles, fields, or fundamental laws. The implications depend on what future observations reveal. If spectroscopy confirms that many of the 300 candidates are genuinely at high redshift and genuinely massive, the pressure for new physics increases substantially. If most turn out to be lower redshift or less massive than estimated, existing physics probably survives. Science works by pushing theories until they break, then building better theories. The 300 galaxies are definitely pushing. Whether they'll break our theories remains to be seen. James Webb's discovery of 300 mysterious galaxies raises an unsettling question. If we missed these objects completely until now, what else are we not seeing? Space is vast, and our observations cover only tiny fractions of the sky. The universe might be filled with impossible objects we haven't found yet, because we weren't looking in the right way. Consider how Webb found these galaxies. It required infrared sensitivity that previous telescopes lacked. Hubble looked at some of the same regions and saw nothing. The objects were there all along, broadcasting their presence, but invisible to instruments that couldn't detect their stretched, redshifted light. How many other types of objects are currently invisible because we're using the wrong tools? Extremely distant quasars might be lurking beyond current detection limits. We found quasars out to redshift 7 and beyond, but these are the brightest ones. Fainter quasars at even higher redshifts could exist in large numbers. They might reveal that supermassive black holes formed even earlier than we thought, adding to the timeline problems. Primordial galaxies, even older than the current record holders, might be waiting for discovery. Webb can see back to potentially 50 million years after the Big Bang under ideal conditions. What if galaxies formed even earlier, at 50 or 100 million years? Such objects would be incredibly faint, requiring extremely long exposures to detect, but they might exist. Dark galaxies represent another possibility. These hypothetical objects would contain large amounts of dark matter and gas, but few stars. With minimal star formation, they'd produce almost no light. Current telescopes detect the galaxies by their starlight. Dark galaxies would be effectively invisible. We'd need to detect them through their gravitational effects or by observing the gas itself. Failed galaxies might also exist in abundance. These would be systems where dark matter halos formed, but star formation never got started efficiently. They'd contain some gas, but remain mostly dark. Finding them would require innovative techniques like radio observations of neutral hydrogen or gravitational lensing surveys. Then there are the exotic theoretical objects that observations haven't yet confirmed or denied. Black hole stars, if they existed, might be more common than we realize. Neutron star clusters could have formed in the early universe under special conditions. Strange quark matter might exist in forms we haven't recognized yet. Intermediate mass black holes remain mysterious. We know stellar mass black holes exist, formed from collapsing stars. We found supermassive black holes in galaxy centers, but intermediate mass black holes weighing 100 to 10,000 solar masses are rarely observed. The early universe might have produced them in significant numbers. They could be abundant, but hard to detect without active accretion. Population 3 stars. The very first stars, made entirely of hydrogen and helium, have never been directly observed. Theory predicts they existed and should have been extremely massive, but maybe some survived longer than expected or formed later than we think. Finding an actual population 3 star would be revolutionary. Primordial gravitational waves from the earliest moments after the Big Bang might be detectable with future instruments. These waves could carry information about physics at energy scales we can't reach in any Earth-based experiment. They might reveal processes that fundamentally shaped how the universe evolved. Exotic dark matter candidates could produce observable signatures we haven't recognized yet. If dark matter occasionally interacts with itself or with ordinary matter in specific ways, those interactions might create signals in telescope data that we've been misinterpreting or dismissing as noise. Even weirder possibilities exist. Some theories predict cosmic strings, topological defects in space-time left over from the early universe. They'd be incredibly thin, but enormously massive. Finding one would confirm aspects of theory that remain highly speculative. Pockets of false vacuum, regions where space itself remains in a higher energy state than our surroundings, might exist. These would be incredibly dangerous if they expanded, converting surrounding space to the true vacuum state. But if small and stable, they could persist undetected. The point isn't that all these exotic objects definitely exist. Most probably don't. The point is that the universe is vastly larger and potentially far stranger than the portion we've observed. Every time we build a more capable telescope or develop a new observational technique, we find unexpected things. The 300 impossible galaxies taught us that the early universe was more active and more capable than we imagined. What will we learn next? What other assumptions will be challenged by future discoveries? Webb will keep watching for years, perhaps decades, if its mission continues as planned. With every passing year, its surveys will reach deeper into the cosmos, mapping wider stretches of the sky. And soon, a new generation of telescopes will join the effort, each adding fresh eyes and new powers to the quest. The stream of discoveries is only beginning. Somewhere out there, likely in more than one place, exist objects so extraordinary that seeing them would upend everything we think we know. They're waiting for the perfect instrument, the perfect wavelength, the perfect moment of observation. Some may challenge our understanding even more profoundly than those first 300 impossible galaxies. Time and again, the universe proves itself more inventive than our theories, more varied than our models, and far stranger than we dare to imagine. The impossible galaxies are just another hint that the cosmos still holds its greatest secrets close. And what comes next may be beyond anything we've yet conceived.